Yeah, change gears. We're talking about electrons, electron configurations, mostly Lewis structures. So valence electrons, let me get periodic table down. Okay, so we left off, we're doing Lewis dot structures. A couple of specific rules for Lewis dot structures. One is that everything except for hydrogen, helium, lithium, and beryllium wants an octet. Hydrogen, helium, lithium, beryllium, duets, 2 electrons each. Okay, so we're placing electrons from a pool of valence electrons. We get that pool of valence electrons from we figure out how many valence electrons from the periodic table, and then we're adding up all of the electrons, whenever this goes over, for the atoms that make up the molecule, adding up all those valence electrons someday. Eventually, there it goes. So adding up all these, so for this ion now, we have carbon, we have nitrogen, and we have a 1- charge. So this is the trick with ions. If we have carbon, nitrogen, so you can remember valence electrons, so carbon's in, this is 4A, has 4 valence electrons. Nitrogen is 1 over, has 5 valence electrons. And then we add in 1 more valence electron because of the charge on cyanide, on the CN. Then that gives us 10 valence electrons. Then we subtracted these 2 electrons out because we wrote a bond in here. And then that left us with 8 electrons left over. And then when you're placing those 8 electrons, you want to try and make as many octets as you can first. And then after you've made all your octets, count and see if things need more electrons, and you move them around from there to get octets. So any electrons that are in bonds are shared between the 2 elements. And then the last step for ions is that we write them with brackets, put a little negative charge outside the brackets. So that matches the charge that's up here on the formula. Super quick recap. So for this ion, remember our first step is to write out a skeletal structure. Part of that is determining which one's going to be the central atom. If there's 3 or more atoms, one of them will be the central one. And it's almost always the one atom that there is one type of. So in this case, though, we have 2. So we're not going to have a central atom. So we can just write them next to each other. Cl and O. And then for any molecule, we have to have at least 1 bond. So we're going to start with just 1 line between them. All right, so that finishes off skeletal structure. Now we count up how many valence electrons we have. So I like to list out all of the elements that are part of the molecule. So how many valence electrons is chlorine bringing to the table? 7. So it's the column number. So, and it's the 7A. So not every periodic table has it on there. If it just has, you can always write it on yourself. 1, 2, or 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A.
And that's just however, that's how many valence electrons they have in that column.
Yep. And then you'll notice here, like this is 3A, but it's also 13, so you can subtract 10 from these ones and still get the same thing. So for chlorine, it's got 7 valence electrons. So how many does oxygen have? 6. 6 valence electrons. And then because we have a charge, this minus on the CLO. So for that charge, we add 1 electron for every negative charge. So we're going to add 1 electron here. If we had a positive charge, then you're removing electrons. So we're going to have a total of 14 electrons. And this is where you're start relating some of this stuff back to the Lewis structure worksheet. So the VEs, that's your total number of valence electrons. That's what this 14 is. So that's VE. Then we subtract out electrons for all the bonds that we've already made. So because we have just one bond, every bond is made up of 2 electrons. So we subtract 2 electrons. And on the Lewis structure worksheet, that's BE. So bonding electrons.
Can we just do 3 bonds like right off the bat? Since it's going to be 14 that we're going to be using.
Well, we're going to have 12 remaining electrons. So that's the RE. Oh, wait, did you say 4 bonds?
Yeah, you know how you did that connection right there? That
Mhm.
equals 2 electrons? Can
Yeah.
we just start with 3 and then fill in the rest? Since we know if there's...
You don't know if it's going to be... don't know yet if it's going to be a triple bond. I mean, yes, comparing this to the...
Yeah, you know how right there we did 1, and then we did 2, and then we did 3.
Yeah, so here we started out, though, we had fewer electrons to start, so we had 10. So even though this is good, like, yeah, you should try to see patterns in these things. So we have 2 atoms here, and we started out with 1 bond, and then we placed electrons, but the number of starting electrons is different. So we had fewer electrons to place. So if we wrote down 2 atoms here, it had a 1- charge, and we ended up with exactly the same number of valence electrons here, the structure will end up the same. But because we have a different number of electrons, we're going to get a slightly different structure.
Are the BEs always 2?
No. The BE is always 2 times however many bonds you place in the skeletal structure. So we'll see some more examples of that. But also here, want to note that the RE is remaining electrons. So that's how many electrons you have left after taking out the bonding electrons from the valence electrons. And then you want to place these so that you form as many octets as possible. As many octets as possible. I was trying to think of a better way to word that. So like start with 1 atom, give it all the electrons that it needs to get an octet, then move to the next atom until you run out of electrons. And always start with terminal atoms. So atoms only have 1 bond. In this case, these are both terminal, so it doesn't matter which one we start with. I'm just going to start with chlorine because it's on the left. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that uses up all of our remaining electrons. So now this step, we want to check and make sure that all of the atoms have the number of electrons that they want. So for most things, it's 8. For hydrogen, it's 2. Lithium and beryllium will also be 2. Helium doesn't really form bonds, but it also only wants 2. So you can look at this and count 2, 4, 6, 8. And the bond counts for both atoms on either side of the bond. So 2, 4, 6, 8. They both have octets. So this is the correct Lewis structure. And then because it has a charge, we use brackets and then put the charge outside the brackets, saying this whole thing inside the brackets has a 1- charge. So there's 3 examples of charged compounds that are on this Lewis structure worksheet.
The 12E are the electrons that are on the outside, not the ones that connect them to.
Correct. And that's why we subtracted out these bonding electrons, because that's these 2 electrons.
But the total we're supposed to have is 14.
So we count the total number of electrons, 2, 4, 6, 8, 10, 12, 14.
Yeah.
Any other questions? All right, now everybody's favorite exceptions. So exceptions to the octet rule. This is one that you're not going to see in this class. Nitrogen has an odd number of electrons. It only has 5. And so phosphorus also only has 5. Because of that, you get odd numbers of electrons in their Lewis structures. So here, nitrogen has this 1 extra electron. Also here, 1 extra electron. Well, I guess it's the same structure drawn twice, but 2 different ways. Usually compounds like that will have a charge, so it adds in 1 more electron, or you'll have more than 1 atom with an odd number of electrons. So, because the other one that's odd is chlorine. Fluorine, chlorine, bromine, iodine, they all have 7 electrons. So you usually end up with odd numbers of them because you usually have even numbers of electrons. Almost never do you get single electrons. The other significant exceptions, and they are on the Lewis dot worksheet, Lewis structure worksheet, are aluminum and boron. So aluminum and boron both only need 6 electrons. So BH3, formula for this would be BH3 or AlH3 will have just 6 valence electrons, and that's fine. Those are the only exceptions. Ah, dang it. I always forget about these. There's also these, yeah.
We're gonna go over this later, right?
Yeah, I do want to go over some of those. So, sorry, these other exceptions, which the only one that you really need to worry about is this one, because that's on the Lewis structure worksheet. The exceptions to the octet rule, you can take a shot at these ones in the back, the expanded octet ones. You can go ahead and do those. They're not very tricky, but I'm not going to grade those. So you don't have to do them. The only ones, phosphorus, sulfur, I think arsenic and selenium also can have expanded octets.
You said the ones down here?
Yeah, you can cross those out. Okay, so those are the exceptions. Sometimes, if we write Lewis dot structures, so for this one, I'm going to run through this quickly, just to get to the point of this. So we have sulfur dioxide. So there's sulfur, oxygen, 2 of those, 1 of these. Each has 6 electrons for a total of 18 valence electrons. And then we used 2 bonds, so that's 4 bonding electrons. So then our remaining electrons, we're going to have 14 remaining electrons. Now this does, or this is a place where we have terminal atoms. So which of our atoms here are terminal? It means it's at the end. So yes, thank you. On top of it with the analogies today. So we want to place these 14 electrons on 1 oxygen first until it has an octet, and then switch over to the other oxygen, fill that out until it has an octet, and then if we have anything left over, it'll go to the sulfur in the middle. So we'll start on the left, 2, 4, 6, and then I move over to the other oxygen. 8, 10, 12, and then oxygen now, that oxygen now also has an octet, and then I put 2 more in the middle. So if we look at these, both the oxygens have octets. They have 8 electrons each. Sulfur only has 6. And so our solution to this is to make a double bond. And it only needs 1 double bond. But which oxygen do we choose to make the double bond? And the more important question is, as you're right, it doesn't matter. So you can make it from the left one, we can make it from the right one. So let's just, for the sake of illustration, we're going to take it from the right one. And so we'll get this double bond oxygen, and we get that. But we could have taken them from the left, and you get the equivalent structure with the double bond on the left side now. So both of these are correct. And for this class, I only expect you to write out one of them. If you take Chem 1, you'll have to be able to write out all the possible resonance structures. But they happen whenever you get the situation where it's essentially the same thing, because I could take this and I could spin it, and it is the other one. And so they're equivalent. In reality, you don't get one double bond on one side and a single bond on the other side. In reality, you get a combination of the two. So that double bond is not actually a full double bond, but it's not just a single bond, it's somewhere in between. It's kind of like taking dog breeds, or if you take this like German Shepherd and this white lab, mix those together, you get a hybrid that has traits of both. So in a resonance structure, that double bond has some of the properties of a double bond and some of the properties of a single bond. So either of those Lewis structures are good. And so those bonds are the same, end up being the same, and they have intermediate strength and intermediate length between a double and a single bond. So remember, when we go from a single to a double bond, it gets shorter. Go from a double bond to a triple bond, it gets even shorter, and they also get stronger. It's DNA. Like the fact that it's a double helix? Oh, I see, with the dogs. No. The analogy doesn't stretch that far. I'm sure it breaks down at some point. Sorry, both of these are equivalent, and you can write either one with this double-sided arrow in between them to say it's this one or that one. So, writing out a Lewis structure. So which atom's going to be in the center? Nitrogen.
I think this is where I'm going to show you.
You're on top of it so far. So we've got nitrogen, oxygen. How many valence electrons does nitrogen have? 5. So it's not the atomic number. It's the column number. Oh, oxygen has 6. And then we have a charge, so we add one more electron in. So total of 12 electrons. And then we already used 2. We already used 2 bonds, which is 4 electrons. So remember, valence electrons, bonding electrons, and that's 8 left. Those are our remaining electrons. And then we pick an oxygen, and we start placing electrons there first. So 2, oh wait. Sorry, I messed up here. I didn't do 2 times 6. So that's 12. So it should be a total of 18 electrons. I was like, we're going to run out of electrons awfully fast. So 2, 4, 6, 8, 10, 12, 14. So this, do I want to draw that line? So remember how I said if you have the same number of atoms and you end up with the same number of electrons, you'll get the same structure? So if we look at this, we have 14 remaining electrons. We have oxygen, nitrogen, oxygen, 3 atoms. If we look up at sulfur dioxide, oxygen, sulfur, oxygen, ended up with 14 remaining electrons. So we're going to get the same structure. So same thing here, where now we've got both oxygens have enough electrons, but nitrogen needs 2 more. So we can form either bond, and we'll have Could do the bond on the left or on the right. I say it's either of these. Don't forget these brackets.
So the brackets, you have to do it because you have that negative charge?
Correct.
If not, you don't need a bracket.
Correct. If you have a charge, then you need to have brackets. Yep.
How do you get the 4E? Or BE?
This form?
Yeah, I don't understand.
So we write the skeletal structure. And this is kind of the hard thing about like looking at this after the fact, is because we've already placed all this stuff. But when we started with the skeletal structure, we put oxygen, nitrogen, and oxygen. So let me do this in a different color. Oxygen, nitrogen, oxygen, like that, with bonds in there. So before we even counted the number of valence electrons, we had those bonds. And so this 4E accounts for the fact that we already used 4 electrons to make bonds in the skeletal structure. Alrighty. Sorry, we're moving fast. This is the getting in now to the last part of the Lewis structure worksheet, because there's multiple things that you have to do on here. All right, so you have to get the valence electrons, the bonding electrons, remaining electrons. Then you do your whole Lewis dot structure. You don't have to have all of the steps in here. So like if you do, like I did here, and you have to like redraw this, you don't have to redraw it. Just erase one of these lone pairs and draw in the double bond. If that makes sense?
Yeah.
So how would you, sorry, how would you know if it's gonna, so if it's a, if you're gonna put the double bond, is that only if you run out of spots to put electrons on the terminal thingies? Or how do you know if you're gonna have like a double bond or a triple bond?
So we put a double bond or a triple bond when we've run out of electrons. And then we're borrowing, so here we're taking electrons for this top Lewis structure. We're actually taking 2 of these electrons and then adding them to make another bond. And so we know we need that, because this is 2, 4, 6 on nitrogen. And it needs 8.
Would we be able to do the first one together? And that's it, first one?
Hopefully we'll have time to do a few of these. So everything needs to have 8 electrons, right? So here, before we did a double bond, this is only 6.
Oh, so then we have to borrow from the oxygen.
Yeah, so we took one of these and then put it in there, and now nitrogen has 2, 4, 6, 8.
And then the oxygen still has 8 too.
Right, because these are still part of, oxygen still has those also. Yep, they're now holding 2 hands instead of 1 hand. Pair of hands. Analogies get weird sometimes. All right, so the last part of this is, what do these things look like in 3D? So the shape down here is going to be, and we'll get to it's called the molecular geometry. So when you take those atoms and arrange them and bond them together, what shapes do they form? And there's really only a few basic shapes. And valence shell electron pair repulsion theory is why they form these shapes. And essentially it is, electrons don't like each other, so they get as far away apart as possible. So these electron groups around a molecule will repel each other. So if we have a molecule that only has a central atom and then 2 atoms, so like, I guess that one's not a great example. Well, there's an example on the next slide. Then they'll get all the way on the opposite side of the central atom. If we add a third one, now they have to spread out, and they break sort of into thirds, kind of like a pie chart. If you add more than that, things start getting 3D, and you get more complicated shapes. Now for VSEPR theory, it's the other way to say this, VSEPR, each of these counts as one electron group. Not one electron, not one pair of electrons, but an electron group. So lone pairs, this doesn't really help to highlight all those. Lone pairs, single bonds, double bonds, and triple bonds all count as one electron group. So the repulsion between the negative charges of the groups on the central atom determines the geometry. So here's where we got two groups. So for carbon dioxide, there are double bonds between the carbon and the oxygens. And then this is one electron group, and this is one electron group. And we only care about the electron groups around the central atom. Doesn't matter that oxygen's got lone pairs out here. Those don't do anything to determine the shape around carbon. These ones don't do anything either. So the furthest distance that you can get apart, kind of like if you're trying to get as far away on Earth from somebody as possible, be on the opposite side of the Earth. So if you really, really hate one person in particular, you move to the other side of the Earth. And if you're directly on the other side, that's 180 degrees apart. So that's what oxygens are doing here, opposite sides of the carbon. And so this is called a linear geometry, because if you go from this point, through this point, through this point, it makes a line.
Also, auxiliary can't be together. You can have OOC.
You would not have OOC, no.
You might all right?
We're just talking about how these oxygens are spread out around. So you wouldn't get like oxygen here, carbon here, and then like the oxygen up here, or even the oxygen, like it wouldn't be closer. They get as far apart as possible. This is the idea here. I don't think I need to pull up a simulation for this one. It makes a straight line. I think this one's pretty easy to understand also. So now if instead of just one person, you become bitter enemies with another person, now the three of you all hate each other and you want to be as far apart as possible on Earth. So now you're not, the farthest away you can get is sort of at thirds from each other. So there's going to be one person who's that way on Earth. There's one person who's, I guess I should point down. But there's one's over there, and you're all spread out by 120 degrees. And because if I move any closer this way, then I'll get closer to that person, and I don't want to do that. So I'm going to stay here. If I move any further this way to get away from that person more, I move closer to the other person. So they're sort of locked at these 120 degrees. This is what I was saying, it looks like a pie chart.
So what happens if like one of the persons you hate comes into like your 120 degrees? Like, are you guys fighting to the death now, or what?
That's when it is.
Yeah.
So
That's what I'm thinking here. I just.
So if this one moves that way, this one will move that way, and then this one will move that way. They'll just keep chasing each other around, but never get any closer.
All bark, no bite.
All bark, no bite, exactly. Cowards, the lot of them. So this is called trigonal, so three, trigonal planar, because it's flat. It is like a pie chart flat, right? That's as far apart as they can get.
It looks like a fidget spinner.
It does look like a fidget spinner. Same geometry as the fidget spinner, or at least one with three sides. Okay, so 120 degrees. That's three electron groups, and there's a chart for these. Now, what happens if we add a fourth person into the mix? Now it's like a.
Kill one of them. That's all the option.
Now we've got this more of a 3D shape. Let's see, where's my. I have way too many things open. Uh-oh. Okay.
That's because we're talking about electrons, huh? But then if you add a proton, they'll be friends.
Yes.
Proton electrons are friends, electrons are enemies.
Yeah.
Okay, so let's put this into projector mode. All right. Oh, wow, that's.
Hold on. Is this gonna be how I do my marshmallows and toothpicks?
This is a visualization. So again, I'll post this link on Canvas somewhere so you can find this. This will help you see what you're trying to make with your toothpicks and such.
So that's a yes.
So this is, yes. You cannot just take pictures of this, like I said. Can't just take pictures of these. So this is the CO2, linear. So you turn it like this, right? It's a stick. Straight line. If I add another bond, that's trigonal planar. You can like look at it on the axis here and it's flat. They're spread out 120 degrees. If I add one more, this one on the end pushes the other ones down and away. And so from any angle, like if I go to any of these, it'll look the same. Well, we can, but that's getting beyond what we're going to do. Okay, so that's this tetrahedral shape. So when I say I want things to be 3D on your extra credit models, it needs to look like this little tripod. It needs to be able to stand up.
You wanted us to stand the project and take a picture of it.
Yes. Just take a picture of it. Yeah.
We choose our own elements.
There's a list on the end of the Lewis structure worksheet. I didn't print that part out. All right, so here, this is 120 degrees, and so this is the reason that it pops into this 3D shape, because we've got this extra space that we can work with.
Does the central molecule have to be different color?
No, they don't necessarily have to be different colors. So this angle, if we just did this flat, and I can't actually, forgot to switch it. So if we just do this flat sort of cross like this, the maximum distance between these is 90 degrees. And that's not far enough, because if I take one of those, like I showed you, like this, right? That one standing on top, you can get larger than 90 degrees. So they can get farther apart. And that angle ends up being 109.5 degrees. Almost 20 degrees more. And this is called a tetrahedral. And this is what happens when you have 4 electron groups that hate each other bitterly. Okay. Now, the rest of the shapes sort of come either from a tetrahedral or derive out of a trigonal planar shape. So what happens if I change this bond instead of being, this one of these groups, instead of it being a hydrogen, pluck that off and leave it as just a lone pair. So that lone pair has the same repulsion as the other things, the other electron groups, so it's bonded atoms. And now we have a difference between the electron geometry, which is still a tetrahedral, and the molecular geometry. So this is actually NH3. So when you draw the structure, you'll get a Lewis dot structure that looks like this. But I want you to write the molecular geometries for each of these. So the molecular geometry is trigonal pyramidal, and the difference is the electron geometry includes all the electron groups. The molecular geometry only includes atoms, and it leaves out lone pairs. But that lone pair exerts the same repulsive influence as a atom would, right, as another bonded atom.
So for
what do you mean by the lone pair? Didn't it just go to the bottom, the hydrogen? Instead of being straight up, it went to the right?
No, now there's only 3 hydrogens. So if I take this guy, take off one of these, and put a lone pair on there.
How do you get that lone pair?
You can't see them. There's like, I've done this before, so I know where the buttons are, but for whatever reason in projector mode, they're...
No, I'm saying like, where did you get them? Like,
Oh,
is that?
this would be from drawing the Lewis dot structure. So if you do the Lewis structure, yeah. So this is like going, if we go back up to like this one, this lone, that's a lone pair. Those 2 electrons that aren't part of a bond, but they're still around the central atom. Except this one would be trigonal planar. Or actually, no, this one would be bent. Okay, so that's if we take off one of the hydrogens. We can take off another hydrogen and replace it with the lone pair. And that's actually the shape of water. Which is a movie? The Shape of Water? Sorry. The electron geometry is tetrahedral still. We still have 4 electron groups But now we have 2 lone pairs and 2 what we could also call bonding groups or atoms. And so this gives us a bent shape. So the molecular geometry for this is bent. So over this, if I take off another one of these hydrogens, oh wait, this way, and replace it with a lone pair, now it's a bent shape. So where linear makes a straight line, bent is a bent line. But it's still essentially a tetrahedral, now just with 2 lone pairs. So this is the chart that you'll want to learn how to use, because I will give you this chart on the exam. I'm going to cut off these examples so you won't have those. Oh, I do. So I'm going to cut off these examples, but you'll still have electron groups, bonding groups, lone pairs, the electron geometry, angle, and the molecular geometry. So the way you use this is you draw out a Lewis dot structure, and let's use, I'm going to do NH3. Okay, so this is NH3. This is what the Lewis structure would look like. So how many electron groups are there? 4 electron groups. So any bond, whether it's a double or a single, double, or triple bond, counts as 1 electron group. Lone pairs each count as 1 electron group. So we have 4 around the central atom. Remember, that's all we care about. So we have 4 electron groups. So that means that it's going to be one of these 3 options. The next one is bonding groups. Actually, let me write this out. So electron groups, e.g. Bonding groups. So how many bonding groups are there?
There's
3. 3 bonding groups. And then how many lone pairs? So it's a lone pair of electrons. So 2 electrons together makes up 1 lone pair. So there's just 1 lone pair. So now we can look at this chart and say, okay, we've got 4 electron groups. This is electron groups at the top. And then we have 3 bonding groups, 1 lone pair. And then this first one is the electron geometry. That's not what you're going to write down on the Lewis structure worksheet. What you will write down is trigonal pyramidal, because that's the molecular geometry. It's the shape of the atoms.
Okay, but are we supposed to try to do octate, or we're not doing octate on these? We're still doing octate?
Oh, octets?
Yeah.
Hydrogen only needs 2. What do you mean octets for this?
On all this, aren't we supposed to do the 8? Make sure they all
Yeah.
have 8 or whatever?
Yes.
Yeah.
But for hydrogen, it only needs 2 electrons. That's a
The rest are missing dots. Right?
yeah. Well, these are hydrogen, so they only need 2.
For the first one on the Lewis dot structure, it says like that too, that's just a fluorine bonded to a fluorine.
Yep. So if we're going to predict geometry using VSEPR theory, you have to first draw a correct Lewis structure, then determine the total number of electron groups around the central atom, then determine the number of bonding groups and lone pairs, and then you can use the table to figure out what the molecular geometry is. So I will give you that table to use. So this one is actually a great example, because which atom is the central atom? Oh wait, it says N. Nitrogen's the central atom. Sorry. So nitrogen's the central atom. Then one side's going to be oxygen, the other side's going to be chlorine. So what do we do next?
So chlorine has
7 electrons. Nitrogen has 5 electrons. Oxygen has 6 electrons. So it's a total of 18.
There's 2 bonds, 4 total.
Yep, 4 electrons there for that. 14 equals the remaining electrons. So now we can start with terminal atoms. So start with chlorine, 2, 4, 6, 8, 10, 12, 14. Make as many octets as possible first. We don't actually need to know this rule for the rest of it. Huh.
Can you do the nitrogen and octane too?
The nitrogen needs an octet too, yeah. So for this molecule, this is a rule of thumb. There aren't any on the Lewis dot structure worksheet that you actually need this rule for. In general, these main group elements want to have as many electrons and bonds as they do their group number. So otherwise, there's no way to know. So because it's not the same thing for chlorine to make a double bond or for oxygen to make a double bond. In this case, oxygen is going to want to make the double bond.
Why?
So if we count, this is what I was saying. So oxygen has 1, 2, 3, 4 electrons and 2 bonds. And it's also in group 6. So 4 electrons, 2 bonds, that's 6 electrons and bonds. So oxygen likes to have 2 bonds and 4 electrons and lone pairs. Chlorine has 1, 2, 3, 4, 5, 6, 7 electrons and bonds. It's in group 7. Nitrogen, group 5, 1, 2, 3, 4, 5. That's a Chem 2 thing, really, but it's a really easy rule. They want to have as many bonds and electrons as they do their group number. So, how many electron groups does this have? 3. So 1, 2, 3. And we're only counting those around the central atom. So it's 3 electron groups. How many bonding groups are there? 2.
I don't know why it's 2. Because it just equals to the chlorine and oxygen?
Yeah. And then even double bonds count as 1 bonding group. And then how many lone pairs? 1. And you'll find the number of bonding groups plus the number of lone pairs will always equal the number of electron groups.
The 2 dots above the...
Mm-hmm. So 1 lone pair. So we got this 3, 2, 1.
So that equals 8.
So yeah, we go to 3 electron groups, 2 bonding groups, 1 lone pair, bent. Oh man, this chapter is so long. Okay, this is what I'm going to do. Instead of doing SO3 2 minus, let's do ClO3 minus, because that's one of the, or ClO3, 1 minus, because that's one of the ones on the Lewis structure worksheet. So Cl is going to be in the middle. 3 oxygens. Oh, this is 7. And then there's a charge, which is 1 more electron. And that's 26 electrons. So that's your number of valence electrons. And then we've got 3 bonds, so 6 bonding electrons. Twenty remaining electrons. So then, still want to place these around terminal atoms first.
We're placing 26 total, right? Well, minus the 6 that we already have in.
Yeah.
So 20.
So there's 20 left, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. That's not what I wanted. And I know sometimes you want to Google things just to make sure that you got it right. If you Google these, you'll get it wrong.
Put your phone down and we.
Because then what's the point? Okay, so if you Google this, you get it wrong because it'll try and put double bonds in here, and that'll give chlorine more than an octet, but it's already got an octet, so it's fine. Just leave it alone. Don't know about, is it oxidation numbers? No, it's not oxidation numbers. I haven't taught it, so I don't remember what the term is. Okay, so we want to know what the molecular geometry is, though. So we need to know the electron groups, bonding groups, and lone pairs. It's not. I know what you mean. It's kind of like an inverted umbrella. Yes. So, but that has a different name. So how many electron groups?
So there's 3.
Yeah, so it's 4 electron groups because the lone pair. 1, 2, 3, 4. Did you lose a set of electrons somewhere? And then 3 bonding groups and 1 lone pair. So if you go look this one up, it should be trigonal pyramidal.
Oh,
Like NH3. Okay, so this is actually going to have some sort of 3D shape, but how do we represent that 3D shape on a flat piece of paper? A little bit of notation. There are hashed lines, straight lines, and wedges. So the straight lines are in the plane of the paper. Hashed lines are projected into the paper. So you're saying whenever there's a hashed line that it's actually, you're looking past the paper a little bit. It's on the other side. When there's a wedge, so a solid triangle, that's coming out of the paper towards you. So that is what those mean. I think we could do it. This chapter is long. Chapter 12 is, or chapter 11 is very long. To make a note that chapter takes 3 days. So if you combine oil and water in a container, they separate into distinct regions. So there's something about the water molecules that causes them to bunch together and not mix with the oil molecules.
is that why we use soap to wash our hands?
Yes, you're going to learn why soap works. So if we look at a water molecule, this has that bent shape. And so we can draw this oxygen like this, and then I'm going to draw hydrogen here, and then there's a lone pair and a lone pair. And so even though these are covalent bonds, they don't actually share the electrons evenly. The oxygen is more of a hog for those electrons. And so the electrons, I'll use yellow because electrons, are in this cloud, but they're really more around the oxygen than they are around the hydrogen. And so this oxygen takes more than its fair share. And because electrons are negative, this then has a slightly, and that little squiggly thing means slightly negative. This other side where there's fewer electrons is slightly positive. And this is determined by a property called electronegativity. So oxygen is more electronegative, and you can think of electronegativity as how much that the atom wants to steal other atoms' electrons, how much they want to hold on to them. So electronegativity uses a relative scale where fluorine is the most electronegative. And this next graphic is terrible on the projector, so I apologize in advance. I'll try and draw some stuff. Oh no, it's not this one, it's the next one. So this unequal sharing, you can kind of see it with all these dots, right? There's more dots around oxygen than there are around hydrogen, so that makes it slightly negative, while the hydrogen's slightly positive, and we call this a dipole moment. So a dipole means that it has two poles, right? Di means two, and one of them's positive, one of them's negative, like either ends of a magnet. So that's in this bond between hydrogen and oxygen. For covalent bonds, which are in our molecular compounds, they have a polar covalent bond. So when there's a great or a moderate electronegativity difference between the two atoms, like hydrogen and oxygen, the more electronegative element has more of the electrons. This is the one that looked really bad. Can hardly see. Yeah, you can't even read any of this. Okay, so this is fluorine, and it has an electronegativity of 4.0. Oxygen is right here, and it's 3.5. Hydrogen is here, and it's 2.1. And the height of those boxes, if you can even kind of see the height relative to each other, is the electronegativity. It's not optimized for projectors. So there's three possibilities. We can either have the same electronegativity between the two atoms in the covalent bond. So if you have two atoms of the same element, the electronegativity is exactly the same. So they're sharing those electrons equally, and that's a nonpolar covalent bond. If you have a large electronegativity difference, this is the second option, right? So either they're the same or there's a huge difference, then the electron is not just unevenly shared, it's completely transferred. So that's any metal reacting with a nonmetal. It's going to be an ionic bond. So you're completely transferring the electrons. The other option is somewhere in between, kind of like Goldilocks. So if there's an intermediate electronegativity, then you get polar covalent bonds. And the difference in electronegativity is kind of just a rule of thumb. You have this table. So from 0 to 0.4 is going to be pure covalent. From 0.4 to 2 is polar covalent. And larger than 2 is ionic. So that means they'll completely transfer the electrons from one atom to the other. So if we're going to classify these, if you have a bond between an iodine and another iodine, what's the difference in electronegativity going to be? 0 or this? Yeah, they have the same electronegativity. So that's a polar covalent, or sorry, pure covalent. This one, we don't even need to look at the chart for this. For cesium and bromine, cesium is a metal, bromine's a non-metal. So what kind of bond is this going to be? Ionic. Now the only remaining option is polar covalent. But we can also calculate it from this other chart. Oxygen's 3.5, phosphorus is 2.1. So phosphorus is 2.1, oxygen's 3.5. So the difference between those is 1.4. So if the difference in electronegativity is intermediate, so anywhere from 0.4 to 2, that's going to be a polar covalent bond. So they're still sharing electrons, but kind of unevenly. The important thing here is to not necessarily, it's to know that there's a way to do this, but it's more important to know that in a lot of bonds, the electrons are shared unevenly. So one of them is going to be a little bit positive, the other one's going to be a little bit negative.
When you look it up in the microscope, that's what you would see, these shapes.
You have to have a very special microscope, yeah. So even though you might have a polar bond in a molecule, it doesn't necessarily mean that the molecule as the whole thing is polar. So we talked about water as having hydrogens like so. There's also electrons like so. And so this has a dipole moment, which is represented, we can represent as an arrow. And the little plus on the tail here means that side's positive and the other side's negative. But you could also have something like carbon with 4 hydrogens, and those are going to be polar covalent bonds, just barely. But because they all cancel, the polarity of each of the bonds cancels out because they're all directly opposite from each other. So that molecule is nonpolar. So what matters more is whether there's some sort of asymmetry to the molecule that allows one side of it to be more polar than the other side. And you can think of this as kind of like a tug of war. And if you watch one of my older videos at the time, Squid Game was really popular, and there's a whole Squid Game tug of war scene. So you use that analogy. But if you have two sides here playing tug of war, right, they're going to cancel each other out because they're exactly equal in power. And that's what you get when you have two of the same bond. So carbon-hydrogen bond is going to have the same dipole moment. So that's going to be nonpolar. You can try and do this, and if you have a great spatial awareness, like if you're really good at like manipulating shapes and things in your head, you can do it this way and just think about the shape of the molecule and think about whether or not the bonds are polar and try and figure out if those dipole moments cancel out. That is the hardest way to do it. But if it makes sense to you, that's fine. It will work. Because what you're trying to do is find, like this, for water, hydrogen-oxygen bond is polar, but since they're bent, they're not pulling against each other. They're both kind of pulling in the same direction. So together, their dipole moment is going to add up to something like this. And we'll get to the easy way to do polarity. So this molecule is polar because they're not pulling against each other. They don't cancel out. There's this whole chart. So there's all these different scenarios. The flat ones are easiest. So if you have a linear molecule, they're pulling directly against each other. If it's nonpolar, trigonal planar, now you've got 3 groups of tug of war. They're still sort of pulling, if they're all the same strength, against each other. So this one is fighting against the force of these two, and you go around the circle like that. Polar molecules have these forces, but they're pointed at odd angles away from each other. And even for the tetrahedral, if these are all the same, then they'll pull against each other. So this is the way the book that says to determine polarity. And like I said, you got to have a good grasp of like spatial manipulation, mental spatial manipulation. You use VSEPR theory to determine the molecular geometry, and then determine if the molecular is symmetrical, and then think about how the different bond strengths affect each other, and it's a whole headache. So again, Mrs. K's alternate method for determining polarity, much easier. You do still need a Lewis structure. You draw your Lewis structure, and then you check for two things. And if both of these things are true, then it will be nonpolar. So there are no lone pairs on the central atom. If that's true, that's one of the things. If the atoms bound to the central atom are all the same, have the same electronegativity, then it's nonpolar. So we can draw up a lot of examples like this. So one of those would be carbon. Let's do carbon tetrafluoride, and I'm just going to give you the Lewis structure here. And just like with molecular geometries, you're looking for lone pairs on the central atom. So are there any lone pairs on the central atom for this molecule? No. Are all of the atoms bound to the central atom the same? Yes. So this is nonpolar. If I change one of these, to hydrogen, now, are there any lone pairs on the central atom?
No.
Sorry. Lone pairs on the central atom is what matters here. Are all of the atoms bound to the central atom, they have the same electronegativity? No. So this is polar. Because it can only be polar or nonpolar. So if there's any lone pairs, water, for example, are there lone pairs on the central atom? Yes, it's polar. So lone pairs on the central atom, it's polar. If one of the attached atoms has higher electronegativity than the others, it's going to be polar. You could even draw up this scenario where it's two hydrogens, two fluorines, right? No lone pairs, but not all of the atoms attached to it are the same, so it's still polar. So this one is nonpolar, polar, polar, polar. Okay, we did that. We did examples like all of those. So the reason that oil and water don't mix is because polar molecules will snap together like magnets. And so you could take a bunch of marbles and put them together, and if you had magnetic marbles will all stick to each other, and they'll push away or push out any non-magnetic marbles. So oil and water work basically the same way, where the water molecules are all very attracted to each other, and they don't like the nonpolar molecules that don't have that same polarity to act like a magnet. And the reason that soap works is because a soap molecule has a polar end and a nonpolar end. So the nonpolar end will stick to the grease, and then the polar end, if you're running water over it, so you've got soap on there, the polar end will stick to the water as it's flowing by and rip the grease away. And it'll pull all of the grease into the liquid from the polar end.